Hello everyone, welcome to our tutorial on supervised visual learning. Can you hear me okay? Okay. My name is Anelia Angelova, and with me here is Vondrick, and jointly with Pierre Sermanet we are organizing the tutorial. Unfortunately, Pierre got injured his foot, so he would not be able to attend CVPR, and I will finish and give his talk. This tutorial is composed of 4 parts. I will give an introduction, then Carl will talk about feature representations from images and videos. Then we have a coffee break, and after the break, we'll talk about unsupervised learning from 3D, and we'll finish with self-supervised learning for robotics. All the slides will be put up on our tutorial webpage later today. Okay, so to get started, let's talk about what do we mean about regarding unsupervised visual learning. What we will be focusing today is on learning feature representations that are useful, and also on learning direct outputs. For example, you see examples in robotics where you can directly learn grasping without any supervision. And in particular, we'll look at several cases in which you can have unsupervised learning. You may be able to learn from videos or images, from transformations, for example, from rotations, or times or sequences of images, learning from 3D, where we use structure constraints from the 3D world, and learning with self-supervision, very specifically in robotics, where you can have one sensor supervise the actions of the other, or you can use your own actions or interactions for your own supervision. And in general, why are we interested in unsupervised learning? Unsupervised learning is learning without manually supplied labels. And clearly, the biggest advantage is that it is capable of providing a limited amount of training data. Also, supervision by itself may be expensive and slow. It may take years to obtain a data set. It's hard to define the labeling task. You may need several iterations. You may need to apply some quality control over the labeling process, and it is expensive. Also, supervision may be inaccurate. So here, a task in which, for an input RGB image, you would like to learn the depth. If we use a depth supervision from a sensor, you can see to the far left how the supervisory signal is incorrect. There is a pole that's not present in the actual image. And this is happening because there is a time delay between the sensors, the two sensors. Also, it may be inaccurate in the sense that the supervision may not be the most optimal for a task. To the left, you see an object with a bunch of bounding boxes, that are useful for grasping, provided by human. But they may not be the most adequate ones, or may not be even the best ones. And some work which we'll discuss today, Pinto et al. Discovered that you can have the robot supervise itself by grasping and verifying it's a good grasp, and learn much better grasp. And also some subsequent work in which, by introducing adversarial learning, they obtain even better and more stable grasps. And also in tasks such as action recognition, supervision may be subjective and open to interpretation. When does the action start and stop? What constitutes an action? Playing golf, is it when I start the swing, or is it when I enter the golf course? So it's kind of not well defined. But also, supervision is important. We are not saying that we can solve all the problems without supervision. And when and how much supervision you need really depends on the task. And there are some tasks which you may not go without supervision. So, for example, for pedestrian detection, you really need supervision to know the very hard cases and to be able to do a very good job by learning. In tasks like fine-grained classification, you naturally need supervision, and here it's even, the tasks are so hard. In this task you need to say, for example, what subcategory of mushroom this is, or what breed of dog, and so on. And in this task it's even hard to find reliable supervision. And also, one supervision signal may be worth thousands of unsupervised examples. For example, in reinforcement learning, one demonstration could be really helpful to guide the process and so on. So what we're saying is that supervision is important, but we'd like to discuss in this tutorial the potential of unsupervised learning and how it can help. And so some benefits we already discussed, that unsupervised learning provides neighbors for free. It may provide better features for some tasks, as we'll see in the tutorial. It may speed up tasks, such as in the reinforcement learning for robotics, we can also demonstrate. We are trying to look at different sources of supervision, and self-supervised or unsupervised learning can help further with weekly and semi-supervised learning, as well as open the possibility for learning on the fly and learning on the web. So let's go a little bit over the basics. So unsupervised learning is learning without labels. And the most classical example is clustering, which I'm sure everybody is familiar with. You have a number of points in space, and you want to cluster them, usually by providing a criterion. Do you care about finding the most dense clusters, or do you want to find the maximum separability, and so on? So here, for example, a K-means algorithm. Another very fundamental approach in supervised learning is density estimation. You have, again, a number of points in some space, and you would like to model, usually by probabilistic modeling, of their density, so that you know if you sample a point, what's the probability of its being part of this event. So, for example, this plot shows the old faithful grazer and eruptions, and if you build a probability density function, you would see that you would rarely need to wait more than 100 minutes to see a grazer, for example. So it will give you an idea of how this becomes. And of course, dimensionality reduction is really, really important in supervised learning. Here the goal is from data that's in a very high dimensional space to learn such a lower dimensional representation so that it satisfies some criterion. And typically the criterion is that maybe the similar points stay together, or another criterion could be so that the new dimensionality representation is capturing the highest variance of the data. For example, PCA is exactly that criterion. So here, the LLE, locally linear embedding, is being visualized for input dimension of the number of pixels in each of these images, and lower dimensional space, for example, 2D. So you can see that they cluster by the expression. And here the criterion for doing this particular lower dimensional representation is first in the high dimensional space, for each point, find a set of neighbors and find the linear combination by which a point can be expressed as a linear combination of its neighbors. So basically the first equation you're optimizing with respect to values. And then now that you know how each point relates to its neighbors, you would want to find new representation in lower dimensional space, let's say Y, where you want to preserve this weight, this relationship between points, basically keeping the weights fixed. And now you optimize with respect to Y, and you get a result like that. And there have been many ways in there. Also, sparse coding is one very prominent approach for unsupervised learning. Here, the idea is if you have a set of data that comes from a particular distribution, for example, natural images, can you find a set of vectors, an overcomplete set of vectors, so that each image can be represented as a linear combination of of those vectors. And if you have an overcomplete set, there are many possible combinations that you can use. So Oshausen and Field formulated this by minimizing or trying to penalize for the number of vectors that you can use for each decomposition. The most incredible thing is that they run this algorithm for natural images or patches from natural images, and the basis functions that they recover are those, which this is done in 1907, it's one of my favorite papers, and as you know, nowadays deep neural networks uncover those features very easily. Another very, very famous algorithm for supervised learning, of course, the autoencoders. You have your data in high-dimensional space. You want to find a smaller dimension representation such that you can, using it, you can now recover the original data. As described here, where here is a very simple one layer for encoding and one layer for decoding. So you're learning a function, let's say f, which given the input x recovers again x. So that's identity. It's a very trivial function. It's not very interesting to do unless you are restricting it and saying, I would like the dimensionality of the hidden layer of the unknown dimensionality to be smaller. And in this case, this is exactly a dimensionality reduction techniques similar to previous dimensionality reduction techniques. And also, if in this same architecture, you don't give a requirement over the number of hidden layers and hidden units in the hidden layer, and you let them to be as many as you want, kind of an overcomplete basis if you want, then you can impose a sparsity, and you would recover an algorithm similar to sparse coding. And of course, autoencoders, in the simple picture I showed you, may not be as interesting and meaningful unless you add many layers of nonlinearities. For example, here from the input image, you have added 4 layers until you try to find a lower dimensional representation, and then you're trying to have another set of layers to find the decoded image or approximation of it. And so this is work by Hinton and Santulinov, in which is the first one to demonstrate these multi-layer embeddings that are actually nonlinear, that they can find very meaningful and very useful lower dimensional representations, and their predecessors to deep neural networks, of course. And one key interesting fact here is that in the beginning, as you know, these were very, very hard to train, and they proposed a method in which they trained them layer by layer. And so the highlight of this tutorial, we hope to be able to convey that supervised learning is useful, that you can do learning from videos, images, and so on, as Carl will talk right now, and we'll show you how you can learn from 3D constraints and also learn from self-supervision and interaction with the environment. Thank you, and so now Carl will talk about learning feature representations from images and videos.
Back. Raise your hand if you can't hear. Can't hear? It's a joke, but maybe people can't hear. Oops. All right. So I thought I'd start with collecting little data, and I just made up this experiment on the spot. So let's see how it goes. But if everyone could stand up, if everyone could stand up, you just flew in. You could do a little standing. Okay. And so the experiment we're going to do is you can sit down if you haven't spent this much money labeling data. So if you haven't spent $1, at least $1 labeling data, you can sit it down. And I want to take pictures on this. No, 30 of your papers to your lab or some through directive. And I want to get pictures so we can post on social media, do a poll. Okay, so you can sit down if you haven't spent $10. I saw a few people sit down. That must be pretty cheap data. Okay, $100 you can sit down. If you haven't spent $100, you can sit down. I haven't thought this through. I don't know how high I have to go. All right, $1,000. If you haven't spent $1,000, you can sit down. Okay, so $1,000 is a critical point. Okay, well, now we're at $10,000. Okay, I guess all of academia sat down. Okay, what were we at? I say 10,000? Okay, so now we're at 100,000. Wow. 1 million? Okay, 10 million. You're still standing. 100 million? People in the back are standing, but I don't think they get the joke. Okay, right. So people are spending lots of cash just on trying to label data, and this is not scalable, right? We really want to scale up to the complexity of the world and tackle many tasks, right? And I think unsupervised learning is a promising way to get there. So today, what I'm going to discuss is kind of an overview of some of the recent work in representation learning from images and video. And it's just going to be kind of a high-level overview to kind of get you acquainted in what people are doing. And hopefully you can see what some of the limitations are in the field. So you can improve them, obviously. And so the main question here, right, is how do you learn these representations without using any labels? And I the way I like to view this is, the computer vision field for a long time has been focused on, learning to see, right? We try to create these models that are learning to see by we label our data, and we try to train a model to predict those. And what today I want to focus on is a slightly different viewpoint, which is rather than learning to see, what we do is that we just watch the world in order to learn. So we don't have to train machines to see. What they should do is just observe outcomes, observe consequences, and try to learn internal representations just using natural outcomes in the data. And so there's a variety of signals that people in the field have been trying to use for learning these representations. I think one of the best one to start with in this tutorial would be about using context. And one of the first papers, how do we get rid of that? How do we get rid of that bar, I guess? Oh, it's loading. Okay. Okay, well, so I have to remember this. So one of the first works in this direction of trying to leverage the natural context in data, right? So every image you have, every video you have, there's context for free contained inside these images, and we can try to use this context to create a supervisory signal to train models at large scale to learn representations. And so one of the first works to do this is by Carl Dorsch and Alyosha Efros. The names are below the loading bar. And what they did is they created this context task where you just take an image, you break it up into pieces, and what you try to do is you try to predict the relative position between these two pieces. So here in the example of the cat, right, you want to predict that you know for free where each piece came from in the image, because images all have this context built in. And so what you can try to do is train a model that is actually trying to predict, given these two pieces, what's the relative position here. And so the answer is shown on the right in red there. Here's a few more that you can try to do yourself, right? So where those two bus pieces are supposed to be arranged, and where the train tracks. And kind of the high-level argument here is that if you can do that task, right, if you can understand that the ear is to the top left of the cat, you've learned something about the nature of images, right? Maybe you've learned something about cats, that the ear typically is to the top and not to the bottom. And so what was super cool about this work, I guess the Wi-Fi is not very good. No surprise. It's okay. I'll try to remember all of the names. Okay. And I think the Wi-Fi. There's probably some big. All right. So what was super cool about this work when it came out is that it could then, they just train it on this context prediction task, just predicting the relative position between two patches. And then they get this representation internally in the network that they can use as a generic descriptor as a feature. And so here's a figure from their paper where on the far left, they're taking an image patch that's not seen yet as a query, and they're showing retrievals under the features that emerge automatically from this model. And so the second column is just if you use random initialization, usually just use Gaussian noise as your weights in the network. The middle is if you pre-train on an ImageNet, and the right is on the context prediction path. And so what's cool is that in this space that emerges, right, you automatically get some semantics. These features are encoding a distance, right, that you can use that actually have some semantics in it. So for example, the wheel, or in the very first row, right, is in the context prediction task is actually retrieving more wheels, right? The other one I like is the second row with the legs, right? So in the random initialization, it's kind of matching the low-level statistics, like there's two bars, right? There's kind of a strong horizontal edge. But in the context prediction, it's actually learning, it's not just about bars, right? It's actually about legs. And so it's cool that this is all coming out for free. There's no labels in this task. So the kind of another work that took this direction even further is saying, let's not just do context prediction, but let's actually create a whole jigsaw puzzle we can train the model to solve. I apologize, I remember the names, but I can't pronounce them without reading them. And so here the task is what the input is going to be the middle column here. And so you're going to train a model that's going to take in each of these different patches, and it's just trained with just the classification to classify what is the correct permutation that you want to make in order to recover the true solution. So you want to try to predict how should I permute these tiles in order to recover the image on the right. And so kind of the argument is the same here, right? But what's going on is that you're saying there's some context in the image that we can display signal. Oh. Yeah. Let me just stop loading. No, it's video stream. Yeah. Okay. Okay, right. So before we were talking about that there's this context prediction task. We try to predict the relative position between two patches. And to increase the complexity of this task, where you can essentially expand this and say, let's actually try to solve a whole jigsaw puzzle, where you try to take, again, different puzzle pieces here that are scrambled in their position and try to predict what is the permutation in order to recover this. And what's super cool about this work is that the representation you get when you actually visualize the different layers in this, you start to get these units that are responding to these different semantic concepts. So kind of the first layer that you get, this is kind of what we usually call comp1 in the network. This is all trained without any supervision. Is you get these kind of, these oriented edge detectors. It kind of learns like Hog, right? But just without any labels. As you start going up the network from comp2 to comp3 to comp4, right? These units start to emerge that are capturing some higher level concepts. So this one I think is trained on ImageNet. So there tends to be lots of pictures of dogs, right? So a lot of units are specializing to the dog nose and dog feet and so on, right? But just notice kind of what the different kind of each row here is showing a different unit, and you can kind of see the low level variation, right? That these units are capturing. So it's not just clustering on things like color or basic texture. It's actually starting to get at something higher level, like actually what is a nose, right? Learning what is a nose without any supervision. What's kind of impressive is that if you take these two models, that you train them on these either context or the jigsaw puzzle task, you get these features that we can then transfer to a new task, for example, classification, detection, or segmentation. And so what this table is showing here is showing kind of different performances by different models on these three ET tasks. The first row is if you train with ImageNet, you have access to whatever, millions of labels, right? And so on classification and detection, you're getting 78 and 56 respectively. If you randomly initialize your model and just train directly on this task, right? Remember these tasks, these downstream tasks have much less labeled data. Right? This is trained on the Pascal data set, Pascal VOC data set, which is typically, I think, around 10,000 examples. So if you randomly initialize and just train with those labels, your performance drops quite drastically. You're operating around 53% classification, 43% for detection. This would be JP now. So what's cool, and I think what's exciting, and I think what's got a lot of people in the area excited, is that if you pre-train on these tasks, right, you actually get these features that are starting to get close to what if you were to pre-train on ImageNet. And so the jigsaw puzzle task and is getting to 67%, not too close yet, but I think the gap will close as we get towards the end of the tutorial. So kind of one hypothesis that I think we can make here just from these two data points, right, is that as we increase the complexity of this pre-training task, the representation from the model seems to be improving, right? By going from just a two-file patch to a whole jigsaw puzzle, right, our performance is growing by large amounts. And so, kind of we can extrapolate this, and we can say, well, let's not just solve a jigsaw puzzle task, but let's actually try to solve an imitating task, where given the image on the left with some hole blacked out, or whited out in this case, can we train a model that tries to fill in that hole, right? So it's kind of like in Photoshop, there's the content aware fill, right? Can you learn to do that end to end in the hopes that this is going to learn representations internally? I think the argument kind of makes sense, right? Like, if you just look at that hole, when you kind of think what should go in there, well, you recognize the windows around the sides, and now you want to just, put another window there. So here's a couple more results from this work. And so, it does a very good job. Kind of the loss that they're using here is a least squares loss on the pixel intensities plus it's an adversarial loss. You know, it's trained on ImageNet. And you can see it does a pretty good job at actually trying to fill in what could be there. So when we try to look at what happens to features, we try to evaluate how well do these features do when we evaluate them on downstream tasks like classification and detection. You can see the results here in yellow. And so, right, this in-painting task is getting around 56% versus 44% in detection. And so what's going on here, right? It's not, we've increased the complexity of this task via performance. It seems like a much more harder task to solve than just do a jigsaw puzzle. So why is, you know, performance dropping here? And so, you know, it is a tutorial, so I guess we have to have a pop quiz, which is, you know, why would the richer supervision, right, yield this worse performance? So to answer this question, there's another workshop going on right now about trying to interpret what neural networks learn. And essentially, there's, you know, this area within computer vision that what I view is building like a microscope in order to look at what are these neural networks learning inside. I think this is a really valuable tool for us in self-supervised learning, because we actually try to understand what are the failures of this and why are they working the way they do. And so I'm going to highlight a particular paper by David Bao and Boy Zhu, who what they did is they built a kind of a toolkit that takes in a trained model, these kind of arbitrary complex model, and what it produces is what they call a dissection report. And it tells you all these different stats automatically about what's going on inside the model. Is it learning about objects? Is it learning about parts? Is it learning about scenes, and so on? And one of the cool things that you get from this is not only all these different charts that you can interpret, but you can also look at visually what are these representations capturing? What are these different units inside the neural network? What are they learning to detect? And kind of the way they're able to do this is they just kind of the standard trick, you know, now is you just feed in a bunch of images that you've not seen before, and for each unit you try to see where it responds the most. And so here, this is a figure from their paper where they we're just highlighting a few different units that emerge in a model trained with on ImageNet. And so you can see, right, this ImageNet model has a lot of rich detectors for wheels, more dogs, human or baby faces, and cars, right? And so, you know, this is kind of what we get with representation if you have access to large amounts of supervision. So we can also look at what happens internally from a model trained on the jigsaw puzzle task. And so here's what these units are. It's kind of a random sample. Well, random sample by me copy and pasting. And so, right, I think what you should notice is that the units are not quite as semantic, right? But they're still capturing some higher level details, right? You still get this space detector automatically that comes out. For some reason, that's really important to learn about faces in order to solve a jigsaw puzzle. But you also get some features about texture, for example. Now, if we go to the model that's trained on in-painting, right? Here's what the model tends to learn. And you know what you should see is that you're learning some sort of textures, right, about bars and so on. But you get a lot of low-level color detectors, right? And I think the reason why this is because when you do the in-painting task, right? The way to cheat with this is just try to pick up colors somewhere and throw them in, right? If you block out kind of a window here in the curtain, right, try to fill it in, well, yeah, I mean, you're going to get pretty close if you just kind of take the average color around you and put it in there. And so, you know, I think what this highlights is, you know, do you want this representation that's discriminative or do you want it to be generative? And so if it's generative, you have a problem where what you have to overcome is you want to avoid these little low-level details. Oops. Okay, so one of the cool things about this work as well is that they can actually quantify these different units and see what do these different units respond to, right? Are they responding to objects, are they responding to colors or textures? And so here's a plot that from their paper comparing an AlexNet model trained on ImageNet versus these self-supervised models that we've discussed so far. And so the way you can read this plot is basically higher is better. These are more units. This is counting how many units in this model are semantic. So on the AlexNet model trained on places or ImageNet, right? In the blue is showing how many object vectors are emerging, right? And you can see that it's rich of these object vectors. All these object vectors are starting to come out. When you go to the self-supervised models, you're starting to get some object vectors, right? Because we saw them in the visualization, but there's just not as much, right? And so how do we go beyond this? How do we start making these visualizations and these representations internally to actually start looking more like and actually detecting the same number of objects as a fully supervised approach? Okay, so I think the next chapter that I want to take us through is going beyond context, actually starting to discuss color. How can we use colorization as a signal for learning representation internally? And this idea has been discovered independently by several authors in the field. I've listed a few on the slide here. And kind of the basic idea here is to train a model that's going to take in a grayscale image and try to predict the colors from that image. Excuse me. And right, this seems like a really cool idea, right? Because basically, ever since the color camera was invented, basically every photo you can get has color in it. And so this is a free source of supervision for training features. And kind of, I think the argument you can make here, right, is that color is kind of correlated with what objects are, right? We know sort of that grass is usually going to be green, sky is going to be blue. A butterfly, there's lots of variation in color, but kind of the typical mode here would be kind of, when I think of like a prototype of a butterfly, and then it'd be this orange color. And so if we can split up the image, so what we do is instead we basically split up the data, so we're trying to predict color from grayscale and use this as a way to train features. So besides as a way to learn features, I think one of the really cool results from this work is that you can actually go back to these photos that are black and white, and now you can add color to them. So here's some famous photos. This is a result from Richard Zhang and his co-authors, where they take black and white photos, bring up atoms, and are able to predict what the colors could be in this photo. You can see it does a pretty good job, right? It's actually starting to get stuff about kind of the trees and the sky and the water. Here's more famous old photos where we're trying to pick the colors. This colorization task, though, of course, is multimodal. There's, given a grayscale image, there's multiple ways you can colorize the image. These chairs in this room could be, blue or green or besides red. So there's been some interesting work in the colorization community to also try to generate multiple possible colorization. For example, going from a grayscale image here to just not only predicting one colorization like blue, but also what are all the different possible colors that this fish could have. And so I think this is one of the major challenges in colorization is that you actually, it's multiple possible solutions, and so we need to build models that are robust to the multimodal nature here. So colorization to me is I think is surprising at how well it works. I wouldn't have thought it worked, but it does work very well, and it's been replicated across the community as a way to learn features. And so, here what this is showing is on the Pascal data set, where if you just train to colorize as images, and then you just fine-tune it, or you train a linear classifier on top of these features for a downstream task, right? You're starting to get, you're getting 61% on classification, 46.9 on detection rate. So you're testing us quite a bit. That's like what 8% on classification, more than just a random initialization. So there is quite a lot of signal here in colorization that we can use. Okay, this might need a video. Can I go back? Okay, so on the note of colorization, I wanted to, so this is some work that at least I can remember the name here because it's my own name, where what we're trying to do is, you're trying to train a model for colorization of video. So not just in a static image, but can you try to predict a model, you can create a model that takes in grayscale video and is able to predict the color. But what we do is not what I'm showing on the board here. What we actually do is train a model for colorization that is taking in a grayscale frame and one frame of color, and it tries to predict the colors throughout the rest of the video. And so you're probably thinking, like, why would you want them to do that? Wouldn't you ever just have one frame, right? Well, you could, you could colorize one frame. But what's cool about this, and we're going to put this on archive soon, if we ship on archive now soon, is that you get a model for tracking automatically from this. So by training a model to actually try to colorize video by pointing to reference frame, tracking is going to emerge automatically that we can then use for downstream tracking tasks. And so if you're interested in hearing more details about this, there's some workshops on Friday that will be discussing this in more detail. But this is a good segue into the next chapter of this tutorial, which is trying to also use, signals about video in order to learn representations. Okay. All right. So one way to use video, one of the kind of an approach from a few years ago now by Zhaolong and Wang and Abhinav Gupta, the argument that they make is simply this. If you can track objects, right, through video, what you can assume is that, the identity of this object, the class of this object, is not going to change over short periods of time, right? You're still a person if you walk forward a few seconds, right? Maybe you transition over long periods of time, right? You transition from a baby to an adult, right? But over short periods of time, you're going to maintain your same class. And so what they do is they can basically download a bunch of videos from the web and use kind of a standard tracker. I think they use features based off of SIFT here. And what they do is they track all the different objects throughout the video. And then what they can do is they create a training problem where what they want is to turn in embedding such that patches that came from the same track should be closer than patches that are cross tracks, right? So to make that concrete, there's this figure from the paper here, where this person on the bike, right? We want the embedding between these two patches to be closer in space than what we want is if we have between there should be closer in space in between the same person riding the bike and some other random patch. And so, this is a signal that a model can use for free, as long as you have a way to track in your video for free. It could be with some sort of specific base case tracking, for example. You can set up this problem on instances and try to learn these embeddings. So I think this is a cool qualitative result. This is from in the paper. What they show is example ground truth positive pairs that they're able to extract automatically from video. And so you can see here, right, for example, just notice the variation in appearance between these two patches. So the first row shows one pair, and the second row shows the corresponding pair there. And so I think what's powerful about this signal is that we can explicitly teach the model, look how these objects should change over time. So, right, the horse, for example, on the bottom row, and the motorbike on the top row, last column, right, this is how it's going to change over time, and we can actually train it explicitly to be invariant to these types of deformations. So this is one of the earlier works on tracking. This is one of the earlier works on learning representations from tracking. And so, if you can look at how we're doing here. And on classification, we're getting around 58%. So there is signal here that you're able to use. I think what's cool, though, is that if you just look at those numbers, it's very easy to be misled by numbers. So we can also we can basically take out this microscope that the interpretable learning community has been developing and apply it to these self-supervised models here, and see what does this model for tracking learn, right? Maybe we don't need to fine-tune it. Maybe already internally it's learning some features that we can use. And so what's cool about the tracking one is you can see, it's a, right, this is kind of the column showing how many units are interpretable in the tracking task. And it's quite rich. You're getting, a significant number of detectors for objects for free, right? And I guess it kind of makes sense. I think this plot kind of makes sense. It also learns a lot of features for texture, right, which is probably pretty important for tracking. Okay, so there's a variety of ways that people have been using video for learning representation. Kind of another way you can do this is you can try to essentially create a skipgram from video. This is inspired by in the text community on Word2Vec. What we want to do is, if we have a target frame, what we want to learn is that the target frame should be close in feature space to the context frames, but far away from frames that are further away in time. So you just want to say, things that are close together should be similar. Things in time, things that are far away in time should be far away in feature space. And so here's a visualization of the embeddings that you get from this type of signal. So the left is this is a TSME embedding. On the left is from features trained on ImageNet, while the right is on features trained from this skipgram type model. And the colors are corresponding to different categories. So it's hard to see in the back. There's things like board trick or wedding or birthday, parade, parkour, and so on. And so qualitatively, from these features, you can see it's starting to learn some sort of separation between these semantic categories. Kind of extending this, and kind of in similar spirit to trying to do context prediction, you can also try to create puzzles from video, where you can use the natural temporal ordering in video frames in order to solve and scramble them, essentially. You shuffle them, and you try to train a model that can recover the correct ordering. And so here's an example from a paper by Ishan Misra and his co-authors, where they have the correct video and they scramble it up, and you have to train to recover it. So here's a qualitative result, where what you get from the embeddings when you train this way, where the far left is showing the query, and everything else is showing the retrievals, or what's similar in feature space to that query. So the first row is kind of within the video, the second row is across different videos. And so you can see I think what you should notice here is what is this learning? it's learning a lot about pose, right? At least from this visualization. I think it kind of makes sense, right? If you want to know, reorder the frames in a video, right? One important cue is the person walking forward or backwards. Okay, so let's do one more quiz you can think about, which is what low-level features, if any, could the model be using to cheat? So if you train a model to try to reorder the frames in a video that have been scrambled, are there any low-level signals that this model could be using to cheat that don't correspond to semantics? Timestamps? What do you mean? Oh, yeah, there's actually a timestamp on the bottom. Yeah, that's a good one. Any other guesses? That's pretty close. What is it? Yep. So, right. So, in a related paper by Dong Wei, what they do is they train a model to try to predict whether a video is going forwards or backwards. And so this makes sense, right? For some videos, this might be hard, right? If you look at video me speaking, probably it's the same going backwards, right? But if you look at a video of like an explosion or someone cutting a banana or something breaking, right, it's very easy to tell whether it's going forward or backwards, at least on a semantic level. What they found in this paper, though, and I think they make an important observation, is that the model can essentially cheat on this task by looking at the different encoding artifacts from the compression algorithm. So video is so huge, right? And so there's these very hard to see by the human eye, but there are different artifacts that tell you the order of the frame inside different before videos, for example. And so the model can use that to cheat. And so if the model can cheat, you're not going to learn these rich features, right? And so it's very important to keep this in mind when you're developing these self-supervised type approaches. What are the low-level features that you could use to cheat? Kind of some work that we've also done in this area is trying to train models to actually generate video from scratch. This is the GAN-based model that's trained on these tiny videos from Flickr that tries to generate new videos. I won't play them because we go look at the slides. You can also use this model for trying to do video autocomplete. So given one frame or a few frames, can you predict forwards what's going to happen? And you could argue that this is similar to the M painting here, right? Rather than M painting a image, what you're doing is you're trying to M paint a video. And these might be good ways to learn features. So we can evaluate kind of these different approaches on video. There's two of them. We're going to switch to a different task here, which is trying to see how well the representations for video do they come out. And so we can look at the UCF 101 data set. Kind of the time these papers were published, an ImageNet model on UCF 101 action classification was like 91%. Probably right now it's at 99 is the upper bound here. But if you train a model by this, using temporal ordering, right, you shuffle the frames and try to learn features from that, which you then fine-tune on your video classification task, right, you get pretty good performance, around 52%. You obtain a similar performance by trying to generate videos as well. So there's still a long gap right there between what a supervised model can do. You outperform kind of classic features like this. Okay, so I want to mention, because it's related to this, is there's another signal we can use, which is ego motion inside video. As you move around, right, that might be a good signal for learning about features. I think Anelia is going to talk about this in her section. So this will be a forward pointer if you come back after coffee. So you can I think another cool feature you can use is just, in video, things are going to move around, and maybe we can define what objects are by their motions. And so in some work by Deepak Pathak and his co-authors, what they do is train a model to take in an image and try to predict which objects are going to move based off of the optic flow. So if you use a classic optic flow, approach, you can get this other modality for free, and we can train they can train in models for trying to predict whether an object is going to move or not. And what's super cool is that then, even though they train this on video, if they use the optic flow for training, at test time they can feed in a static image, and the model will automatically segment out what are the objects that could then move, right? And so there's no supervision here. We don't have to fine tune it, right? It just internally comes out. And so you can see right here some qualitative results where it's getting the bus or the bear. You can notice one kind of I'm not sure if it's success or failure, it's probably a little bit of both, is, right, because both the two cheetahs can move, they get clumped together. All right. So we can go beyond just using vision, and I think what's cool about video, what's exciting to me about video is video is like really huge, and there's just so much different context that you can use. And so I want to talk about the next chapter here, which is about using sound. And so one of the early works in sound was done by Andrew Owens and his co-authors. And kind of what they did was they created their basic idea was, let's run around Boston smacking things with a stick and recording a video and try to use the ambient sound from that smacking task as a way to learn features. I think they spent a long time trying to smack things until they realized that actually, they could just go to videos from the web, right, and use the natural sound there in order to train. So now they don't have to run around hitting things. So what they did here is they basically take a bunch of videos from the web. They split up the video between vision and sound, and they train a model that tries to take, again, just RGB features and tries to predict sound from the features. From pixels. And they use a feature interface similar to spectrograms called cloakograms to do this prediction task. And what's exciting here is that they can then take this microscope, right, and inspect the model that's trained on sound prediction, and they get these different semantic units automatically, and they're kind of corresponding to what different sounds things would make, right? So babies, for example, probably make a very distinctive sound, so that's going to be clustered together in feature phase. And on the bottom row, they show some example of baby activation. But there's several here, like a waterfall or fields. I think the sky one is particularly interesting because the sky generally doesn't make much sound, so why would it worry about that? But maybe it's correlated with wind, right? There could be correlation, but it could use. So we can also go the other way. What they were doing, what Andrew Owens was doing here, was going from transferring from sound into the vision domain. We can also go the other way, where we transfer vision into the sound on domain. This is some work led by Yusuf Aitar. And what we were doing here was taking a model that's pre-trained on vision and just transferring it, and using it as a teacher for a student model in the sound domain. And so you can train this model that can start recognizing ambient sounds by using vision as the teacher. I think what I like about this work is I think it exemplifies this point of, rather than in labeling data to train, we can just watch the world, right? We can watch video in order to learn about new modalities like sound. And so you can do the same thing with this microscope, I like to call it. You can get these different features, but now these different semantic units, but now in the sound domain. I would play some sounds, but it's really hard to get sound to work. Okay, then, kind of, this is such a simple idea, but it works so well, is, you can combine these two approaches. You don't have to be transferring from vision to sound or sound into vision. You can just do both simultaneously. And this is led by work, I don't know if I can attempt his name, Anelia Angelova. And so what they do here is they basically take sound and vision, and what they're going to do is they're going to, half the time, they're just going to feed the model both the visual stream and the sound stream that correspond to the same video. And the other half of the time, they're going to randomly put a different sound in. And they're going to train a model to say, do these correspond or not? And you can train this model from scratch, right? You get this supervision for free from your videos. And what they show, which is super cool, is that you get these features that work in now two modalities. So you have these features for sound classification that you can use for recognizing these ambient sounds. And you also have these features for vision, which you can use for visual classification. And so here we're showing two different results tables. The left one is just on sound classification. The right is on ImageNet. And I will dive a little bit into this table here, because I think maybe people in the vision community aren't as familiar with this on community. Right, so kind of the previous state of the art on these data sets, it's like trying to recognize ambient sounds. It's like 50 different categories. And they typically, it's very hard to label sound. We typically have around 2,000 examples. So, ComNet trained on that with labels is getting around 64%. What these two approaches are doing, right, they're getting these large gains, right? This is 10% gain every year, and this is, 15% gain over the previous baseline. Right? They're getting this large gain partly, it's partly a little unfair because they're able to train with millions of examples, right? The synchronization between vision and sound is so abundant in video that you can now, train with large-scale data. But, even the reason why I think it's a reasonable argument is that this supervision is free, right? You don't have to label any extra data. And so you're able to get this gain for free. Okay. I want to mention some other work in the sound and vision domain, where we can also just try to, rather than trying to predict sound features, you can, for example, be trying to actually generate the sound so that you can listen to it. And I encourage you to check out their website and actually listen to these sounds. It's pretty cool. So another type of signal we can use for between vision and sound is just misaligning the audio. So while the previous work was taking sound from a completely different video, what Andrew Owens did back again is he just shifted the sound in the sound stream slightly, and he had to predict whether the sound was aligned or not. So it's kind of like when you try to watch TV in your hotel room and the sound is like off sync by a few seconds. It's really noticeable, right? And so that's a free signal you can use for trying to learn features. And so what they're able to do, in addition to learning these features, is you can also start localizing, what objects are making the sound. And so here's a couple of qualitative results from their work, right? Where once the guy's once the axe hits the ground, right? The model's able to predict that that's where sound could be coming from. So in related work led by Heng Zhao, another signal you can use is to mix sound together. And so that what you can then do is actually try to listen to what sounds came from each point in the video. And so what they do is use a very simple signal here, which is that you take video and its corresponding sound. And what you can do is you add two sounds together with addition. Sound is typically additive, unlike vision, so you can combine them together. And what you can do is train a model that tries to predict the original sound from the corrupted sound that's corrupted by noise. And so what they have is this really cool demo online, is that what you can then do is listen to the video, and you can move your giant cursor here and click on different points in the video and just listen to the sound just coming from that source. Here's kind of you can't listen to sounds, here's the static visualization. So this work has been explored concurrently by several people in the community. But here's some work by Ruhan Gao, where they're also trying to do source separation, where you can click on different areas and hear the sound. They take a different approach and try to cluster the sounds first in order to find the correspondence. Here's another work that's similar in spirit. They focus more on human speech. This is led by Ariel Efrat et al. And so what they're able to do is take a model that can take in video with people talking and separate them out into different sources, so you can you know where each sound is. So you can listen to just one particular person. Essentially, if you might click mute on someone you don't like, then could be a politician. Okay. So the next, so I think sound. I mean, I realize you're probably wondering, like, is this self-supervised learning, and here I am talking about sound a lot. But I think what's cool is that you can use these different modalities to teach us about vision. So sound is a promising way because we get access to so much sound from video. But you could also think of more modalities to use too, like touch or taste or smell. Okay, so the next chapter we're going to discuss is kind of what I guess one of the advantages of self-supervised learning and supervised learning is that you don't have to come up with categories, and so categories are very hard to define. And so this next section is also hard to categorize. So we need a self-supervised learning approach for it. But I'm going to categorize it as kind of leveraging just natural invariances in the data. And one cool invariance that you can be using is the fact that you can break up images and create this invariance that you want counts to be the same across broken up images. So this is work led by Mehdi Norozi. And the high-level idea here is super simple, but it works very well. What they do is they take a full image, like this dog, this picture of the two dogs, and what they do is they break it up into 4 pieces. There's 4 pieces that are shown on the right there. And what they train an embedding to do is that the sum of these 4 pieces in embedding space should equal the full image embedding space. And so the idea here, right, is kind of inspired by counting that, right, if you're, for example, you could be counting eyes, right, the model could be learning automatically to count eyes, and what this total sum should be 4, right, but if you just look at the top left corner here, you get to count 2, and as you look at the other pieces, you start to add them up. So one of the cool qualitative visualizations they have is you can actually look at what images have different high counts and low counts. And so, I think this can start to give you some insight into what these models are learning, what are happening inside these features. And so on the left is what you get the high count, right is on the low count. I mean, it's hard to sometimes, read too much in qualitative visualizations, but it seems like that the left side is starting to learn more about objects, right? It's starting to count things like objects, while the right is kind of more textures. Okay, so, right, what are the low-level features that the model could use to cheat in this task? Is there any way you could cheat this task without actually learning about semantics? guesses? So, what the authors found was that there's actually two possible trivial solutions that you need to guard against, which they do. One is that, you know, in this these are counterintuitive, I think, but it makes sense in hindsight, is that one, the model can learn actually what downsampling algorithm you use in order to solve this counting task. And those can leave artifacts that you solve the counting problem. They were able to mitigate this cheat by just using several different downsizing approaches. Another cheat that the model could use is chromatic aberration, which is which happens when different color channels are not in the same focus. And this usually is going to depend on spatially where in the image that the pixel's from. And so this is another low-level signal that you could cheat from. However, I think it didn't matter too much in the result. So another type of invariance that I think you can use is one and that works pretty well is learning by rotating images. And so when you look at these two images here, all of you probably instantly can say, you know, how should I turn this image so that it's facing right side up, right? And how are you doing this? Well, you're probably understanding something a little bit about, you know, you're understanding semantically what's going on inside the image. You're recognizing there's a bird here, and you can use that as a cue in order to say, oh, we should rotate this 90 degrees clockwise. And so this was an idea that inspired Spyros Koudaris and his co-authors to actually learn representations just by rotating images and try to predict what the correct rotation back was. So here's one of their qualitative results, where they're showing the attention map from two different models. The left is trained from ImageNet. This is like you have labels. It's showing what regions it attends to in order to recognize what category it is. The right is showing on this rotation model what region it attends to in order to figure out how I should rotate the image back. And what you should notice here is that they roughly, you know, are looking at the same areas. And so what this is suggesting is that this actually might force the model to be learning to look at the objects and start to recognize the objects in order to rotate the image back. So here's the qualitative. Here's the quantitative results from these two latest methods on counting and rotation. And so you can see the rotation across these different tasks gets very good performance. Right, it's getting 72.9 classification, which is starting to approach 78 at the very top, which is if you have lots of supervision. And so, you know, this gap is starting to close. On detection, the gap is pretty small, right? It's 56 if you have an Allenson model pre-trained on ImageNet, and rotation is in 54. Right? So it's pretty small gap. Okay, so the last chapter I want to discuss here. The last chapter I want to discuss is, you know, how can we start combining all these different methods for self-supervision? Maybe we can improve these numbers more. Kind of a very intuitive approach led by Richard Zane is what they call a split-brain autoencoder. And so in contrast to a regular autoencoder where you try to take in, you know, your data X and you try to predict X, but what they do is they split the X in half in some way. So here they split it based off of colorization, and they try to predict one half from the other half. So the bottom here is showing this decolorization path, while the top is showing, oh sorry, the other way around. The top is showing the colorization path, while the bottom is showing an intensity prediction path. And they show that by training these two jointly, you can start learning features. And so you can get the benefit of both paths right here. And the way they combine the two features here, of course, is just to concatenate them. Some other work that combines different self-supervised approaches is led by Carl Dorsch. I'm not Carl Dorsch, I'm Carl Vondrick. Anyways, so what they're showing here is what happens if you just start combining several tasks together and trains these self-supervised approaches in a multitask framework. And this plot is showing performance on the internet, where the horizontal axis is showing training time. And you can see, right, as you start to add more and more features, performance is of course going to improve. One challenge here is that, in self-supervised learning, we have access to so much data, so it actually is challenging to develop systems that can scale up to so much data. So I think this is another area where we can improve is how do we build self-supervised systems that learn from so much data. So some other work, what it focuses on is what they make is the observation that what we typically do in self-supervised learning is we train a model on one network architecture. For example, AlexNet is what typically people have done in the literature. And then what we do is we use that same architecture for the downstream task. And so that might not be the optimal choice. Maybe you want to change the architecture between the pre-training task and the downstream task. And so what they develop is an approach that actually lets you do this. They try to decouple the two different networks. And what they describe is a kind of a student-teacher approach, where they are able to train a model on the self-supervised task and use it as a teacher for a student model that could be much more complex. So another way to combine these different self-supervised approaches is through a transitive relation. And so here, this is work led by Zhaolong Wang and his co-authors. And so what this is showing here is, right, we've discussed different ways to develop these self-supervised tasks. For example, on the left, we can track an object over time to get a new view. And on the right, we can also use something like context prediction, for example, to say, oh, this car is actually similar to this car because they're both on the road, right? So you get a cross category feature, and also you get a intra-instance feature. And so what you can just naturally do is you can take advantage of the fact that this should be transitive. So because you know by tracking that this is the same in car, and by context prediction you can know that these are similar, we can then track this car and say, well, they should also be similar across the diagram. And so this is another way, that you can mine these positive pairs for training. Okay, so unfortunately, though, after all this, there's still this gap on detection between a fully supervised approach. And so, I think scientifically we're starting to get close, right? The field is on Pascal detection, for example. This gap is around 2.4% still. And so I think we're very close to actually matching a model on detection trained on AlexNet to a supervised approach. Okay, so I wanted to end just kind of briefly on some future directions that we can go as a field. So kind of this diagram here shows generally kind of what is going on in the field self-supervised learning right now is we have a bunch of unlabeled data, we come up with some loss, and then we use that to train a model, right? And kind of what's missing from this diagram, well, that's supposed to be a person. What's missing from this diagram, right, is that there's there's a human in the loop that's coming up with these losses, right? And we can come up with very creative ones. And I think what we have to be careful as a field is that, we've traded in, like, we were doing feature engineering for a while. Now, like, what are we doing? Are we, like, doing loss engineering? Or are we coming up with these new losses that we should solve, right? And so I think we should start thinking about how do we start making these losses that are more scalable. And so some work that I wanted to highlight by Luke Metz, what they've been exploring, I think this paper is at NIPS or Eichler. What they've been exploring is a meta-learning approach where you're trying to learn the update rule from data. So you're still inside the boxed area here. You're still doing unsupervised learning with unlabeled data, but rather than having a human in the loop, which is us, right, fine-tuning on various tasks, you can say, let's try to learn that instead. And so they've been developing an approach that is basically using a little bit of labeled data to try to figure out what is the right update rule for unsupervised learning. And I think this is kind of an interesting direction to go, right? How can we learn what the proxy task is? Right? Rather than coming up with all these different ways of splicing up the data, can we actually learn the right way to splice it? I think another issue that we need to be very careful about is about bias in supervised learning. So, we kind of advantage of supervised learning is that we can just collect huge amounts of data, right? But the downside of that is we can't look through all the data. We don't know what's inside. And so, I think one potential dangerous outcome that we need to be thinking about is, how do we mitigate this bias? How do we understand what biases are being learned by our models? And so I think this is just one thing I wanted to mention. Finally, I think we should, be thinking about tools and ways to actually analyze better what's going on inside these self-supervised models. What are they learning? And I think that's important for two reasons. One is scientifically we should do better diagnostics to see where gains are coming from, so we can actually close this gap more and figure out what is making all of those tick. But I think another reason for trying to analyze these models more is another approach to doing this is not actually fine-tuning at the end of the day, but just hoping that the model is going to learn features internally, learn object vectors internally that we can use directly downstream. So if we can develop the microscope to actually analyze what's going on, maybe we can find these detectors or figure out how to build them make them more effective. Okay, so that's the end of this part. I'm happy to take any questions. Thank you.